Since December 2023 I was busy with experiments with this chip, and it is the 74 HCT 4046 chip, and it's cheap, and it is a voltage controlled oscillator, but also not only that voltage controlled oscillator, but only a phase locked loop. I have by purpose only used the voltage controlled oscillator part. And here is the circuit. I hope it's visible from this distance. It's quite a high distance. It's not say the standard A4 paper, but I will pen over somewhat to give more better ideas about that chip. So I pen over somewhat. Is this an ideal circuit? No, it's surely not an ideal circuit, but it works quite good in, say, as a square wave oscillator, going from 15 Hz up to approximately 80 kilohertz, at least in this demo. Perhaps there are other better waveforms are possible, but I did my best to make it as good as possible to get, say, to the best waveforms. Now it's on 14.8 Hertz. Let me show it. I have to turn, of course, here the frequency switch. Now we are on another frequency, 33 Hertz. I think it's quite good. Now we are on a higher frequency, 235 Hertz. Is the waveform still okay? Yes, it's very okay. 235 Hertz. Higher, 1.4 kilohertz. And you can, with this schematic, change that frequency with the help the help of a potentiometer. I will now turn that potentiometer and let's look. So you see how that works. I have to take some distance. You see, and you can directly see when you have a kind of insight in electronics that this is a very coarse way of changing the frequency. With one potentiometer we go from 8 kilohertz to, say, let me try, 1.4 kilohertz. Anyway, it works quite nice. I've done my best to make it as universal, usable as possible. Let's go to the highest frequencies and look at the waveforms. That's always very, very important. Now we are on the highest frequency. It's 897 kilohertz. What does the waveform look like on that frequency? That's always important. It has changed to a triangle wave. Is that a problem? Well, I don't think it's a problem when you want to do serious radio experiments. By the way, I made a circuit in such a way that even the square wave is as pure as possible. And here is the circuit on the breadboard. Like I make my circuits always, a tin plate glued to triplex wood 3 millimeters to give it a kind of say earth. And this is of course completely experimental. This part of the circuit, it consists of a field effect transistor that buffers in a certain way the output of the chip, and after that a BC547 transistor that also has an effect, of course, also has an effect on the waveform. Let me show at first, say, more or less the key circuit that's here. This is the key circuit, and in this part of the circuit there's no output. Of course, I mean, there is output, of course, here. Pin 2 gives the output signal of the chip. It's a square wave. And here is the frequency setting of that chip. And here is the frequency potentiometer that changes the frequency in relation to, say, the capacitor that you have chosen here. So but I found many problems with that setup. At first, one of the problems was that the waveform got deteriorated a little bit, say a lot of overshoot. And that overshoot could be cured by this part here. Here's the chip again, in fact it's the same circuit, cured by this 22 microhenry coil, and then the field effect transistor, and also here you can correct the waveform via the 10K potentiometer. I've named it BIAS. Well, when you make it you will surely see how it works. And here we have a kind of direct DC driving of the end transistor, the BC507B. By the way, here are the pin connections. Also of the field effect transistor, it's the BF256A. I used that many times anyway, so perhaps it's good to show this again. The chip by itself needs 5 volt supply voltage, and that's realized in a very simple way. This is, by the way, the decoupling unit to the chip, so the voltage goes here to pin 16. This is the BD139. It works as a voltage stabilizer with that zener of 6.3 volts. The output is in the order of 5 volts. This is, by the way, the back side, and this is the front side. So here it is drawn in the back side. And the field effect transistor here also needs, say, a certain voltage. And you can regulate that voltage, and that has a big effect on how the waveform looks like, and that's done here. 12 volt in, decoupling unit here, 4K7 potentiometer, 220 ohm resistor. Here it goes via this wire to the drain of the field effect transistor, and in that way you can set the waveform in a certain way. Hope it's a little bit clear. I think it's a useful circuit. It's not ideal. My idea was to get, say, a square wave oscillator to approximately 1.5 megahertz or 2 megahertz. That did not succeed, but well, it's all experimental. So let's look on all the different settings. Perhaps it's interesting to show in relation to the oscilloscope views. Here is that 10K potentiometer that's here in the circuit. Here, this one, 10K here. Here's that coil that damps, say, the overtones of the oscillator. when that coil is not inserted, you will see a lot of, say, kind of ringing. But this combination, this coil and this resistor helps to avoid ringing in the circuit. So I turn it now. So now we have a sine wave. Well, that's, say, the best saying to tell that it can avoid ringing. So this is a square wave, of course, on the highest frequency. I will especially focus on the highest frequencies because they are most critical. Anyway, now here is the setting, the bias of that second stage. Here, this 470K potentiometer of the end stage. Let me change the bias. Suddenly not everything is gone. So this is a very critical setting, and my advice is, when you want to make such a circuit, use a stabilized voltage supply and measure here the bias of the potentiometer, measure the different resistance values via that node, and then change it by a fixed value resistor combination. Of course, this is a voltage divider. Say here, this is a voltage divider. There's a resistor here and a resistor here. So, and that only can be set very precise when you have a stabilized 12 volt power supply. Otherwise, that will be a problem. So we are on 908. Let's look what this circuit can bring on lower frequencies. And I'm especially interested in the waveforms. So now we are on 86 kilohertz. I think it's a useful square wave for hobby purposes, of course, not professional, but anyway. And here we are on 33 kilohertz or 29 kilohertz. I think the waveform is very good. And has also, of course, to do with the chip. The chip is, in fact, a high quality oscillator chip. Now we go to the lowest frequencies. 1.3 kilohertz and lower 100 hertz approximately. Surely not bad when we look at, say, how good that say here, how the time rises in a very sharp way, etc, etc. And I turn the potmeter now to get to the lowest frequency, and that is approximately 14 hertz. Of course, we cannot expect everything from such a simple circuit, but anyway, it works very nice. Thanks for watching. And when there are developments, I will perhaps give a new video. But this is, say, as it is. So I pan over a little bit now again. And this is, say, the crux of the circuit here. And again, thanks for watching.